Have you ever stopped to think about the hidden forces that are constantly shaping our world? I'm not talking about anything exotic, but something we feel every single day: heat. Today, we're going to dive into how the simple act of heating something up has the power to bend solid steel, help build skyscrapers, and, believe it or not, even make life on Earth possible.
And it all kicks off with a simple little puzzle. If you've ever looked closely at a railway track or maybe a really big bridge, you've probably noticed these small but very deliberate gaps. They almost look like a mistake, right? Like someone didn't measure correctly. But what if I told you that without these little spaces, our entire infrastructure could literally tear itself apart?
These gaps are no accident. They are a critical piece of engineering. They're designed to fight a powerful, invisible force that awakens every single time the sun comes out and things start to warm up. So, what is this mysterious force? Well, to solve the puzzle of the railway tracks, we need to shrink ourselves down, way down, all the way to the molecular level. See, the answer isn't in the massive scale of steel and concrete, but in this unseen dance that every single object around us is performing, right this second.
So, welcome to the world of molecules. Our first big idea is all about what happens when these little guys start to feel the heat. It's the fundamental reason why, as a general rule, hot things get bigger.
The official science term for this is thermal expansion. And really, it's a fundamental principle of physics. When you heat most things, doesn't matter if they're solid, liquid, or gas, they expand. And when you cool them down, they contract. It's this universal push and pull that's totally governed by temperature.
So why does this happen? Well, imagine the molecules inside any object are all doing a little dance. When you add heat, you're basically just giving them more energy. So they start dancing faster, more wildly, bumping into their neighbors and pushing them farther away. This increases the average space between all of them, and voila, the entire object gets bigger.
And this isn't just a theory. Look at this classic experiment. Before you heat it up, a metal ball easily passes right through a ring. But after you apply some heat, that ball has expanded so much that it gets stuck. It's physically larger than it was just a few moments before. Here's the same idea, just with a metal bar. At room temperature, the bar fits perfectly into its little gauge. But once it's heated, it expands in length, and suddenly it's too long to fit. The force is subtle, sure, but it's absolutely immense and relentless.
Okay, so if this force is so powerful, how in the world do we deal with it in our day-to-day lives? Well, this brings us to engineering, where we'll see how this little lab experiment scales up into a massive challenge for huge construction projects.
And here it is, the answer to our opening puzzle. On a really hot summer day, miles and miles of steel railway track can expand by a pretty shocking amount. Without those expansion gaps, the tracks would have nowhere to go. They'd just push against each other with incredible force until they buckled and bent sideways, making them totally unsafe.
And it's the exact same story for bridges. A huge steel bridge also grows and shrinks with the seasons. So engineers don't even try to stop this movement. They just plan for it. They accommodate it. You can see here how one end of the bridge is actually placed on rollers. This lets the whole structure slide back and forth just a tiny bit, safely expanding and contracting.
But sometimes, we don't just work around this force. We actually put it to work. Check out riveting. A steel pin is heated until it's glowing red hot, then it's put in place and hammered down. As it cools, it tries to shrink back to its original size, and in doing so, it contracts with enormous power, clamping steel plates together tighter than any bolt ever could. Pretty clever.
Now, heat doesn't just make things bigger. It can also cause them to make a great escape, changing from one state to another. Let's look at the two ways a liquid can become a gas: boiling and evaporation. They might seem similar, but they're actually fundamentally different processes.
This chart lays it all out pretty clearly. Evaporation? That's the slow, quiet one. It happens only at the surface of a liquid, and it can happen at any temperature. Think of a puddle just drying up on a cool day. It actually borrows heat from its surroundings. Boiling, on the other hand, is fast and violent. It happens throughout the entire liquid, but only at a very specific temperature, the boiling point. And it needs an outside heat source, like your stove.
And here's why you should care. That whole process of evaporation, stealing heat from its surroundings, that is exactly how your body cools itself down. When you sweat, the water on your skin evaporates, and as it turns into a gas, it pulls heat energy directly away from your body, leaving you feeling cooler. It's basically nature's air conditioning. So we've established a nice, clear rule. Heating makes things expand. But in science, for just about every rule, there's a fascinating exception. And the single most important exception on our planet is good old water.
I know, it sounds completely backward, doesn't it? Based on everything we've just learned, it seems impossible. But that's exactly what water does, under some very specific and very important conditions.
This is the famous anomalous expansion of water. See, as you cool most liquids, they just get denser and denser. But water is special. As it cools, it gets denser until it hits 4 degrees Celsius. But then, if you cool it even further, from 4 degrees down to freezing, it suddenly breaks all the rules and starts to expand, becoming less dense. The same thing happens in reverse. If you heat ice-cold water from 0 to 4 degrees, it actually shrinks.
This means that 4 degrees Celsius is the magic temperature where water is at its absolute densest. And this little fact is profoundly important for life on Earth. Think about a lake in the winter. The coldest water, at 0 degrees, is actually less dense, so it floats to the top and freezes. Meanwhile, the warmer, denser 4-degree water sinks to the bottom. This insulates the whole lake, allowing fish and all the aquatic life to survive the winter. Amazing, right?
So, as we wrap things up, it really all comes back to that invisible dance. The exact same principle of molecules vibrating and pushing apart gives us a force so immense it can buckle steel rails, and a strange little exception to that same rule is what protects entire ecosystems in frozen climates.
From the microscopic to the absolutely massive, the principles of heat are shaping our world constantly. It dictates the engineering of a bridge and the biology of a single drop of sweat. It really makes you wonder, what other incredible, fundamental forces are at work all around us, just hiding in plain sight?